Have you ever really thought about what keeps your private information safe online? I mean, there's this invisible shield at work, kind of like a digital bodyguard for your data. It's called encryption. So today, let's pull back the curtain and see exactly how it protects our digital secrets.
Seriously? Think about it for a second. When you buy something online, you're just flinging your credit card details out into the world. How on earth do they get from you to the store without someone just grabbing them? That's the exact problem encryption was invented to solve.
You see, the core issue is that the internet is a public network. It's kind of like a giant open room. Any information you send without protection is like writing a message on a postcard. Anyone who happens to pick it up along the way, a hacker, or what we sometimes call an eavesdropper, can read it plain as day. Okay, so to get how the solution works, we need to know a couple of key terms. First up is plain text. This is just your normal readable message. It could be, "Hey mom," it could be your bank password, whatever it is, it's the data in its original, most vulnerable state. And the whole goal is to turn that plain text into this, ciphertext. Now, it's the same information, but it's been scrambled into a complete mess of unreadable characters. To that eavesdropper, ciphertext is just total, meaningless noise. So, how do we get from A to B, from plain text to ciphertext? Well, you use something called an encryption algorithm. The best way to think of it is like a really complex recipe, a set of very specific rules that scrambles the data. But like any good recipe, it needs one special secret ingredient.
And that brings us to our very first type of encryption. This is the most straightforward way to do things, and it's called symmetric encryption. Let's take a look at how this basic scramble actually works.
The whole idea behind symmetric encryption is really simple. You use a single secret key, just like a physical key to your house. The person sending the message uses that key to lock it, and the person receiving it has to have the exact same key to unlock it. It's simple, it's fast, and as long as the key is safe, it's really effective.
Check out this example. The plain text message is, "Computer science is exciting." The key is just a string of numbers. The algorithm's rule is simple. Just shift each letter by the number in the key. So C gets shifted by 4 and becomes G. O gets shifted by 2 and becomes Q, and you just keep going. The result is complete gibberish unless you have that exact key.
Now, this seems pretty solid, right? You've got one secret key, you share it between two people, everything's locked up. But, and this is a big but, this simplicity leads to a massive critical problem. And there it is. That's the million-dollar question. You have to get the key to the other person so they can unlock your message. But how do you send the key securely? I mean, if you just send it over the same open network, the eavesdropper can just snatch it out of the air. This is what's known as the key distribution problem. And if that one single secret key gets intercepted, well, it's game over. The entire security system just collapses. The eavesdropper has the master key now, and they can unlock every single message you send. It's a huge single point of failure. So clearly, a better way was needed, and that led to the development of a brilliantly clever solution that gets around that whole key sharing problem. It's called asymmetric encryption. Instead of one key, asymmetric encryption uses two keys that are mathematically linked. First, you have a public key. You can literally shout this from the rooftops, post it on your website, give it to anyone and everyone. This key is only used to lock messages. Then you have a private key, and you guard this thing with your life. This key, and only this key, can unlock messages that were locked with your public key. This two-key system, it's the magic behind that little padlock you see in your web browser. Let's walk through this with a quick story about Tom and Jane. In just 4 simple steps, they can have a totally secure conversation, even if someone is listening to everything they say. All right, so first, Jane creates her pair of keys. Then she sends her public key over to Tom. And remember, it doesn't matter one bit if an eavesdropper gets a copy of this key. Why? Because it can only lock things. It has no power to unlock. Now, Tom takes his secret message and uses Jane's public key to lock it up tight. And here's the real magic. Once that message is locked, that very same public key can't open it back up. The only thing in the entire universe that can now decrypt this message is Jane's matching private key. And this is where the system becomes incredibly powerful. Jane can give her public key to Tom, and to Susan, and to Mike, and Megan. They can all use it to send her completely secure messages, and only Jane, with her one private key, can read a single one of them. The key distribution problem?
It's completely solved.
So this two-key system is pretty much the foundation of internet security today. But, technology never ever stands still. This whole arms race between the people making the codes and the people breaking them is heading into some really wild new territory.
See, the math problems that make today's encryption so tough to crack are, well, they're really hard, but they're not necessarily impossible. And the big fear is that someday a powerful quantum computer might just be able to solve them, which would basically break all of our current security systems.
So, what's the next step? It's to change the rules of the game completely. Quantum cryptography doesn't rely on making math problems harder to solve. Instead, it uses the fundamental laws of physics. Now, don't worry about what the polarization of photons means. Just get this. It's a way to encode information where the very act of an eavesdropper trying to look at it actually changes it, which immediately gives them away.
And that's the key insight right there. The technology is based on the laws of physics, not just on math. This is a huge shift. We're moving from security based on really hard math problems to security based on the fundamental, unbreakable rules of how the universe itself works. Which, of course, leaves us with one final fascinating question. For all of human history, it's been this constant battle, right, between the people who build the locks and the people who pick them. As our technology gets more and more powerful, who's going to have the upper hand? It's a race that's still going, and it's going to define the future of our digital world.